Alright, this is part 2 of my frequently asked questions for week 2. I promised a little bit more about how to distinguish different shapes from each other. I got a question from one of you that said, I'm still confused how to distinguish cone from bowl. So I'm going to show one way of distinguishing those two equations from each other. I've put up two equations, z equals x squared plus y squared, and z equals the square root of x squared plus y squared. Surely if there are two equations that are easy to confuse, those are probably two of the ones that are easy to confuse. So I'm going to say a little bit about how to distinguish these two shapes from each other. One thing that you might try is you might try developing contours for each equation by setting z equal to a constant. Let's try that in each case and see what happens. If I set z equal to a constant here, I get c equals x squared plus y squared. I know that's a circle. If I set z equal to a constant over here, let's call that constant something different like d, then I get d equals the square root of x squared plus y squared. And if I square each side, I get d squared equals x squared plus y squared, which is, again, an equation for a circle. So what this means is that working with contours is not the easiest way to distinguish these shapes. You can still do it, actually, by thinking about what happens as the value of c progresses here versus what happens when the value of d progresses here. And there is a way to work it out. But really, I'd like something a lot more straightforward that tells me almost immediately whether I'm working with a cone or some other shape. So let's try something different. Let's try working with cross sections. And I'm just going to do the most straightforward thing that I could do here. I'm going to take one of my variables, let's say x, and set it equal to 0 and see what happens. If x is 0, then I get, for this equation, z equals y squared. Immediately that tells me something about the shape of this graph, because I know that if I draw my coordinate space, this is y, this is x, this is z. I know that when x equals 0, that is when I'm in the yz plane, my graph looks like a parabola. And at this point, because I know that every contour is a circle, I know that the cross sections this way, horizontally, are going to be circled, which means that I'm just going to have a shape that is based on this parabola with circular horizontal cross sections. That means that I have a paraboloid. I'm not sure that's what you meant when you were talking about a bowl, but that's sort of a bowl-like shape. It's a very tall bowl, and it gets steep very quickly. Okay, let's have a look at this shape then. Let's see what happens if x is 0. If x is equal to 0, then my equation becomes z equals the square root of y squared. And at this point, most students say that means that z equals y. But here's where you have to be a little bit careful, because this equation does not always imply that z equals y. Suppose, for example, that y equals negative 1. If y is negative 1, then y squared is 1, and z is the square root of that, which is 1. So y is negative 1, but z is not equal to y. Z is equal to the opposite of y. But what is true in all cases is that z is equal to the absolute value of y. And in general, anytime you see a square root of y squared, you can simplify that to absolute value of y. That's useful to know here because I can tell what an absolute value graph looks like. Okay, assume the same orientation as before. I have, in the yz plane, that is when x is 0, I have a graph that looks like a V shape. And again, I know that all the cross sections this way, all the contours are circles. So this time I know that I'm going to have a cone. Alright, so that's one way of telling the two apart, is if you see the equation, just try setting one of the variables other than z. Try setting x or y equal to 0, and see what kind of figure you get. You may get a parabola, in which case you're dealing with a paraboloid, or you may get an absolute value graph, in which case you're probably dealing with a cone. Okay, so that's one way of telling those two apart. Now, just to give one more example, suppose I give you a different one, a different equation. Suppose I give you the equation z equals square root of 1 minus x squared minus y squared. Okay? This one's a bit trickier. It's harder to recognize this one. Again, let's see what happens if we take contours. Let's see what happens if we set z equal to a constant. In that case, I'm going to get c equals the square root of 1 minus x squared minus y squared. And squaring both sides gives me c squared equals 1 minus x squared minus y squared. And after a bit more rearranging, I get x squared plus y squared equals 1 minus c squared. Now in this case, I know that because this is a constant, what I'm going to have here is likely to be a circle, except I have to be careful this time because if c squared is greater than 1, I actually don't get a circle. I don't get anything at all. So this is only valid. This is only a circle if c is between -1 and 1. And in fact, I can go a bit further than that because I know that if I set c equal to some negative number here, like -1/2, that fits within these boundaries, but I can't have a square root of some number equal to -1/2, at least not the principal square roots, which means this doesn't even work if c is negative. C has to be at least 0 for this to work out. So again, I know I'm dealing with circular cross-sections, or circular contours, that is. But this still doesn't give me such a great idea about how they interact with each other, how the figure progresses from c equals 0 to c equals 1, or from height 0 to height 1. So again, I'm going to try doing something different. I'm going to try setting x or y equal to 0 to find out what the shape of this graph is. So let's try setting x equals 0. If x is 0, then I get z equals square root 1 minus y squared. Squaring each side gives me z squared equals 1 minus y squared. And then rearranging gives me y squared plus z squared equals 1, which looks like a circle, but again, I've got to be careful because I know that z is equal to the principal square root of 1 minus y squared. That is, it's the positive or non-negative square roots, which means that z can never be negative. This is actually not a circle. It is a half circle. It is the upper half circle. So if I try drawing my graph in 3D, I'm going to get the upper half semicircle of radius 1. And then all of my contours are going to be circles. So all my horizontal cross sections are circular. So I should get a hemisphere. It should be a little bit more vertical at the bottom than the way I drew it, but that's okay. So this is a hemisphere. So that's one way of telling different popular shapes from each other, is just try drawing a cross-section and either setting x equal to a constant or y equal to a constant. That is, either parallel to the yz plane or parallel to the xz plane. Contours are useful sometimes. It's just that they didn't happen to be useful, at least not that much in these particular situations. And I have one more question, which was, what are some general equations for different shapes? And for that, I'm actually going to defer to one of the pages in your textbook. If you're using the 6th edition of Multivariable Calculus, take a look at page 702. You'll see a page that has about 9 different figures on it, and that will give you a summary of some of the equations that you really want to be familiar with going forward. So take a look at that. That may be a good thing to study from. But again, memorizing it is tricky because it's easy to memorize things wrong. But if you do the algebra like I just did, it's pretty hard to do that wrong if you're paying attention to what you're doing. So, weigh your options, weigh the difficulty of memorizing versus the simplicity, but sometimes time-consumingness of working things out, and do what's best for you. There will be one more video after this about finding equations of planes.